So far, we've learned about 6 different trigonometric functions. We saw that these functions originate from the relationship between the sides of a right triangle and can be applied to the unit circle. But what else can we learn about these fundamental functions? Today, we'll focus on sine and cosine and examine some of their properties through graphing. First, we'll look at the function y equals sine of x. How would you begin graphing something like this? Just like any other function, we'll input values for x and get an output, y. Since we take the sine of angles, the input variable, x, represents angle measurements in radians. We spent a couple lessons familiarizing ourselves with the value of sine for lots of different angle measures on the unit circle, so let's use that knowledge here. First, we'll make a table of values using some key radian measures from the unit circle, 0 through 2 pi. Now we can fill in the y values. The sine of 0 is 0. The sine of pi over 6 is 1/2, or 0.5, and the sine of pi over 4 is root 2 over 2. Using a calculator, we can approximate that as 0.71. Pause the video now and fill in the rest of the y values using the calculator to get a decimal approximation if needed. Hopefully these values look familiar. Just like in the last few lessons, we can use some memorization and some patterns to recall the sign of every value between 0 and 2 pi. Be sure to check your work before we move on. Now let's get graphing. Pause the video now to plot these points and draw a smooth curve connecting them. Once we plot all these points and draw a line, we get this beautiful wave. But what about over here or here? What does the function look like? Before we plot more points, pause and make a prediction about what you think the graph looks like beyond 2 pi in the positive direction and beyond 0 in the negative direction. Think about everything you've learned about the unit circle and coterminal angles to help you make a prediction. Let's find out. On this side, we want to find y values for x values that are larger than 2 pi. Does that sound familiar? Earlier in this unit, we learned how to find the sine of something like 13 pi over 6 by using coterminal angles. Subtracting 2 pi from 13 pi over 6 results in pi over 6. So 13 pi over 6 and pi over 6 are coterminal and share the same value of sine. So we have the next point. How about 9 pi over 4? Subtracting 2 pi results in pi over 4, so the sine of 9 pi over 4 is the same as the sine of pi over 4. Now, I don't really want to continue this process forever, so do we see any patterns that might tell us what the graph looks like when x is greater than 2 pi? Pause the video now and try to predict the y values for the rest of the table. What do you think? If you predicted that the same values we saw between 0 and 2 pi would repeat themselves, you'd be correct. And what about values beyond those in the table? Well, the repetition continues infinitely. And what about on the other side? What does the graph look like when x is less than 0? Well, this same pattern continues forever in both directions. Now that we know what the graph of y equals sine of x looks like, let's explore some important characteristics of this function. We just noted that the patterns we see in this function repeat in both directions infinitely, giving us our 2 characteristics to note. One is that the domain is all real numbers. The other is that there is a repeating pattern. This is due to the periodic nature of the sine wave. A sine wave, like many trigonometric functions, exhibits periodic behavior, meaning it repeats its values in a regular cycle over a specific interval known as the period. The period of the function y equals sine of x is 2 pi, which means that the function completes one full cycle of its pattern over a horizontal distance of 2 pi on the x-axis, then starts over. While we typically observe the period starting at x equals 0 and ending at x equals 2 pi, no matter where you start observing the cycle along the x-axis, it always takes a horizontal span of 2 pi to complete one full cycle of the sine function. This is a fundamental characteristic of the sine function, reflecting its consistent and repeating pattern. And that pattern includes some important points, like minimums, maximums, and zeros, which also repeat over a specific interval. Notice that in this section of the graph, the function reaches a maximum when x equals pi over 2, and then again at 5 pi over 2, which is a distance of 2 pi. It reaches a minimum when x equals 3 pi over 2 and again at negative pi over 2, which again is a distance of 2 pi. Does this pattern seem familiar? When else have we added or subtracted 2 pi to find another angle with the same properties? When finding coterminal angles. In order to find coterminal angles, we can add or subtract 2 pi one or more times. Just like how the function completes one full cycle after a distance of 2 pi, every time we add or subtract 2 pi, we also reach another minimum or maximum. Let's see if we can find a pattern in this series of x values. The minimums and maximums occur every pi units starting at pi over 2, so we can write this pattern as pi times n plus pi over 2, where n is an integer. The expression pi times n ensures that we are adding or subtracting multiples of pi to get to the next minimum or maximum. This symbol means is an element of, and this symbol represents the set of integers. And what about the zeros? We can see zeros when x is equal to 0 and when x is equal to pi. Again, we can use coterminal angles to find other places where the sign is 0, like 2 pi, 3 pi, negative pi, and so on. Similar to the minimums and maximums, we can represent this series of x values in a different way. The zeros occur at x values where x equals n times pi, where n is an integer. Another notable result of the periodic nature of this graph is that it oscillates or travels back and forth between its minimum and maximum y values of -1 and 1, which shows the function's full range. This oscillation directly leads us to understand the concept of amplitude. The amplitude is the height of the wave, measuring how far it reaches above or below the midline, which is the horizontal line that runs through the middle of the wave, dividing it into upper and lower halves. For the function y equals sine of x, the amplitude is 1. And the midline is the line y equals 0. Now that we've graphed and analyzed the function y equals sine of x, let's take a look at the function y equals cosine of x. Take a crack at graphing y equals cosine of x on your own by filling in the table using the decimal values, plotting the points, and connecting them with a smooth line. Let's see how you did. We can use our knowledge from earlier in this unit to fill in the table and graph values from 0 to 2 pi. Then, using the same patterns we saw with the sine function, we can extend the graph to values larger than 2 pi and less than 0. Does this look familiar? I hope so. It is very similar to the graph of y equals sine of x. Take a moment to compare these two functions and fill in the table of characteristics for the function y equals cosine of x. Let's start with the similarities. First, both functions have a period of 2 pi. They also share the same domain, range, amplitude, and midline. That's a lot they have in common. The difference here is where the cycle starts for each function. When starting at x equals 0, sine starts at the point 0, 0 and completes one cycle at the point 2 pi 0. Starting again at x equals 0, cosine begins at the point 0, 1 and completes one cycle at the point 2 pi 1. This difference means that the function y equals cosine x will reach its minimums and maximums and zeros at different but familiar x values. Sine and cosine functions are like two sides of the same coin. They have many of the same characteristics. However, they're slightly out of sync. While the sine function starts from 0, the cosine function starts at its maximum value of 1. This difference in starting points means their maximums and minimums, as well as zeros, are encountered at different x values. Now that we've seen sine and cosine graphed in their basic forms, next time we'll consider how these functions could vary. What happens if we multiply the function by a number or add or subtract a number? What would the equation be for this function? Nail down the basics of sine and cosine functions from this lesson, and we'll jump into transformations next time. See you then!